right? Okay. Thank you all for coming. As the title, I will talk to you. So this is my hobby. So I'll talk to you about some issues that pop up when you think about communication networks, specifically wireless networks, and more specifically multi-user wireless networks. Okay, and just to give you sort of, let's see. So I was asking if there are a lot of graduate students here, and I guess there are. The reason I asked is I usually have a slide or two where I try to pass on some of the sort of things I learned that I wish some people had told me. Okay, so these are some of the lessons I learned in how to do research. So of course not written in stone, but and so we have here sort of a famous equation, right? And the reason this is here is these are lessons learned from Claude Shannon. And so obviously I didn't know Claude Shannon myself, but I know people who knew him. So what my Shannon distance is 2. I don't know, but so these are lessons from Bob Gallagher actually that he gave at a talk once. Actually, it was a Shannon Day at Bell Labs a few years back, and he talked about this, and I really like them. So I like to tell it to students who are going through research now. The first is go to the source. You read lots of filtered versions of things. It's nice to go back to the source. Like for example, how many of you have actually read A Mathematical Theory of Communication? If you haven't, it's good. I mean, but if you haven't, you should. It has some really nice insights, and he derives the capacity in an interesting way. And he talks about it from a both layman's view and a mathematical view. Secondly, read, but not too much. You can spend your whole life reading. So what do you do when you're not reading? Work problems yourself. Even if the solution exists, think about it yourself. I mean, if it's going to take you 6 months, maybe it's not worth it to rederive the wheel, but if it's going to take a day or two, do it yourself. And the last thing is something that I guess Shannon did, which is abstract the problem into its essential features. Basically, throw away everything that is sort of not critical, and what's left will give you sort of the key insight. Then you can start adding everything back. So sort of for things to think about when you're doing your own research. All right, now we'll get to actually what I'm going to talk about in this talk. I'm going to talk about 3 problems. The first problem is actually is a physical layer problem, but it shows up when you think about multi-user networks, and it's going to sort of try to answer the question: do I want to spread spectrum or not? And if you do, what are the consequences? The second is, so the next 2 topics are basically in sort of problems that exist at the boundary of communications and networking. Okay, so we're going to look at cross-layer adaptive modulation and multi-user diversity in multi-user communication networks. So what's written in parentheses is where I have papers on each of these 3 topics. This might be a little bit hard to find, but I can post it on my website. But these 2, ICC and ISIT, should be easy to find. Okay, so part 1 was to spread spectrum or not to spread spectrum. I'll just try not to spend too much time on this because I want to spend more time on the other 2. But essentially, actually, so this is an interesting thing. I don't know how many of you know the history of spread spectrum. Actually, there was a 1941 patent by this actress, Hedy Lamarr. That was the first patent on spread spectrum. Like when I heard that, I thought that was it's kind of interesting. So it's a composer and this sort of eccentric combination of 2, this actress and composer, and the first patent on frequency hopping for control of missiles, remote control of a missile, and they wanted some secure way of controlling it, and somehow they got this patent. So it sort of, one could say, started here. Then we get into the concept of information theory, sort of founded, if you will, by Claude Shannon. And specifically what I want to talk about today is an information theory view of spread spectrum. And the basis for my work starts with Jim Massey, who tried to put an information theoretic foundation to spread spectrum communication. essentially Massey's contribution was the realization that there are actually different types of bandwidth. The usual type of bandwidth that we know is he called the Fourier bandwidth, essentially the Fourier transform of the the support of the Fourier transform of your signal set. There's actually a different notion of bandwidth, which is how much bandwidth do I need to represent my signal set? And he called it Shannon bandwidth. So it's proportional to the number of dimensions that are required to represent my signal set. And often these are the same, and often they're not. And Massey's contribution was making this distinction and using that to define spread spectrum. The usual notion of spread spectrum is that the bandwidth used is greater than the information data rate. Massey's definition is that the Fourier bandwidth is much greater than the Shannon bandwidth, and then the spreading factor is just the ratio of these two. So this notion is actually true of a spread spectrum system. The interesting thing that we'll get to here. So let's see, one of the lessons learned from Jim Massey is when you do spread spectrum, you increase only the Fourier bandwidth. You, in some sense, don't add new information content to the signal. Okay, so that notion is captured in increasing the Fourier bandwidth. Non-trivial channel coding increases both Shannon and Fourier bandwidth. And I find this interesting that spread spectrum systems do have a large ratio of bandwidth used to information data rate, but the converse is not true. And the example to think about is M-Mary PPM. So you basically want to think about computing the Fourier and Shannon bandwidth and the information data rate, and you'll see that according to this definition, this is not spread spectrum. Okay, so Massey used this notion to look at the effect of spreading. And in a single user system, we look at, so we have a single user on an additive white Gaussian noise with usable bandwidth W, power constraint, average power constraint P, noise power spectral density N0 by 2. And so my bandwidth expansion is W by B, where B is my information bandwidth. Okay? And if I look at the capacity, right, for unconstrained signaling, for direct sequence, where I'm using bandwidth B, the capacity is given by this. That's going to be less than if I don't constrain it to do spread spectrum. And let's look at the ratio of this. So this is going to be our parameter. So let's look at the ratio of spread capacity to the maximum achievable. And you find actually that this ratio can be lower bounded by this quantity here, where I define alpha as this sort of inverse signal to noise ratio type term. Okay, average power over the noise power, and it's the inverse of that. But basically, I find so note that alpha is related to the Shannon bandwidth B. Okay, and as I change the Shannon bandwidth, I change alpha. So as I increase B, I increase alpha. All right. So what does this tell me? This tells me that if alpha, in this equation, if alpha is greater than or equal to 4, this ratio is greater than or equal to 0.9, which means that no matter how much I spread, as long as my Shannon bandwidth is large enough, I don't lose much in capacity. Meaning, I don't lose, the capacity lost due to spreading is not so much. All right, so this is in a single user system, and this is what Massey did. This is sort of, I manipulated this in my own way, but this is the essential result from Massey's 94 paper. So we said, let's see what happens in a multi-user system. They sort of play the same game. You can say, well, remember, in a multi-user system, the notion of capacity is captured by a capacity region. You no longer have one number, right? You have multiple users, and each user has a sort of a limit on maximum information rate, and that leads to a region. So, and the boundary of this region is the analog of the capacity, the number that we had in the single user case. What we're going to consider is one point on that boundary, namely the sum capacity, meaning the sum of all the users' rates. Okay, so that's what I mean here. Okay, this CBS in the multi-user case is every user is spreading, right, by bandwidth expansion n, but I'm looking at the sum of all the users' rates, and it's a function of the spreading sequences assigned to the users. Okay, and I can get a simple bound by just using the same log sum inequality I used in the single user case, and I get this simple bound, which I call bound 2, which actually, you've actually done away with this, right? You get a sort of a tighter bound if you assume random sequences and you make some other assumptions, some large system analysis assumptions. I'm not sure if you all know what I mean when I say large system, but essentially you assume that the system scales in such a way that the spreading factor and the number of users get large, but their ratio remains constant. Okay, so it's like you're scaling it in a fair way, and when you do that, you can exploit properties of large random matrices, and you get this tighter bound that actually depends on the ratio k by n. Okay, so remember, in the single user case, we have the conclusion that as you increase the Shannon bandwidth, you actually can limit the loss in capacity, and I wanted to see if the same thing would hold here, and it turns out this does happen. So here's a simulation with random sequences, 64 users, spreading factor of 96. So remember, k by n is 6. And here's the simulated, sort of just computing those exact quantities and just simulating it. And here are the computation of the bounds. Ignore this bound, so much looser bound. But you see that as I plotted versus alpha, remember, as I increase alpha, I increase Shannon bandwidth, and I get the sort of the same result. Okay, that the loss, so the effective spring, the loss in capacity decreases as I increase my Shannon bandwidth. So Massey's message here still holds. Do some sort of channel coding. Okay, we can actually flip this around, right? You know that channel capacity captures the notion of, for a given signal to noise ratio, what is the maximum rate at which you can transmit. We're going to flip that around, solving for signal to noise ratio, and say, for a given rate of transmission, what is the minimum signal to noise ratio I need? Right? And it's not any different information. It's just it's visualizing the information in a different way.
So there's some sort of modulation encoding that's implicit in this graph.
Yeah.
Right?
I mean, doing ideal coding.
So it's each user uses one spreading sequence.
Each user uses one spreading sequence.
Right, and then he's doing a long block code, routing code book through that spreading sequence, right? He is modulating his code symbols.
Yeah.
So he does single user coding. Right? And is it implied that as a receiver?
No, it's not single. That's fine again. We're not doing.
So there's a joint detection, right?
Mm-hmm.
Are you able to get this result if you sort of decompose that into sort of into MMSE filter followed by single user?
I think you can. Yeah, I think what happens is the threshold on alpha increases.
All right.
No problem. But yeah, I think you get the same result. Okay. So let's flip this around and look at, so before it was the effects of spreading, let's look at the loss due to spreading. This is nothing but flipping the capacity equation solving for SNR. So on the x-axis we have the ratio of k by n. So this is essentially like the system load. Okay? And here we have the loss from Shannon. Okay? And the different curves correspond to different structural efficiencies. Okay? And so this is 2 bits per second per hertz down to 100 bits per second per hertz. And essentially, as I move to the right on this curve, I'm doing more coding and less spreading. And as I move to the left, I'm doing more spreading and less coding. Okay? This is for a fixed bandwidth expansion factor. So there are a couple of things to sort of take away from this graph. Let's see. If for a fixed loss, as I increase my spectral efficiency, let's see. If I fix my spectral efficiency and I move to the right on this graph, I see that my loss decreases, right? But there's sort of diminishing returns. Right? I see that basically moving sort of 1 unit on this graph, the gain decreases as I move to the right. So there's this law of diminishing returns, which says that I want to do coding, but the benefits of coding diminish. Let's say I fix my system load. Right? Remember, I have a fixed bandwidth expansion factor. As I increase my spectral efficiency, my loss from Shannon increases dramatically. Right? So this tells me that if I do spread spectrum at high spectral efficiency, I will be far from the Shannon limit. Now, this is not saying that you shouldn't do spread spectrum. I guess I promised to answer the question to spread or not. I'm going to answer the question, what happens if you do spread? And if you choose to operate far from the Shannon limit, you can. But you might have your own reasons for doing it. Okay. So those are the two views of looking at the effects of spreading and the loss of spreading. And this is a decision one has to actually make in a multi-user communication system. Okay, so it's sort of the message is make some, I want to say mix coding with your spreading. Increase your Shannon bandwidth, and if you spread at high spectral efficiency, you'll be far from the Shannon limit. That's the consequence. I'm going to skip that. Okay, so the second thing, so the next two topics are actually looking more at problems of the boundary of communication and networking. Okay? And actually, we're looking at the first issue in this context also. I'm not going to talk about it here. But it turns out that you can actually address all these three issues in a common problem. So right now I'm looking at them separately. Okay, so for part two, we're going to look at a single user communication system. And we're going to look at adaptive modulation. And what's the cross layer? The cross layer is, okay, so anyway, so adaptive modulation means I'm going to vary the transmission parameters, my parameters of my modulation, power, maybe even channel coding, meaning my rate, according to system state. And I can define my system state appropriately. So for conventional design, we mainly adapt to physical layer, like channel gain. Right? For what I want to consider is adapting to more system states. In this case, both physical layer and high layer parameters, like, and specifically I'll consider network layer parameters. Okay? Sort of delay, buffer, overflow requirements, and so on. And so I call this thing cross-layer design. And maybe it's the first attempt at cross-layer design. Okay. So let's look at the system model. It's very simple. Okay, we have, as I said, it's a single user point-to-point. We have a fading channel, transmitter, receiver, and the main difference from a traditional communication system is I have stochastic arrivals, so I buffer data. Okay, and let's see, so stochastic arrivals into a finite length buffer. For the channel, I have a finite state Markov channel model, and I'm going to make the assumption here that there's perfect feedback, perfect noiseless feedback, instantaneous noiseless feedback from so basically how the transmission parameters are varied is known both at transmitter and receiver instantaneously. You can sort of do things like assume delayed feedback and so on. But for the purposes of this talk, we're looking at instantaneous feedback. Okay. So again, so our mechanism is to do adaptive modulation, so keeping the symbol duration fixed. We vary the transmission power and the constellation size of an MQAM constellation according to both the buffer state, the number of bits in the buffer, the number of packets in the buffer, and the channel state. Okay? And the objective is to minimize the packet loss due to buffer overflow given some average transit power and VER constraints. Okay, so at this point we sort of have to take a step back and say, well, this looks pretty simple. I'm sure people have worked on this. Right? And they have. So let's see what people have worked on. Okay? Let's say I remove this. I have a point-to-point communication system with a time-varying channel. And I've assumed perfect knowledge, so the receiver and transmitter both know the channel. This is certainly related to this, and this problem has been solved. We know how to do optimal transmission over this time-varying channel if I know the channel at the transmitter. You guys know what it is? What do I do?
Depends on how you define optimal, right?
Okay, let's say I want to
So
maximize capacity or the information theoretic capacity.
So which one? So, well, sorry, do you mean outage capacity, or do you mean ergodic capacity?
Ergodic.
There we go. Yeah. Well, I think
Waterfilling?
half the people in the room know the answer.
Yeah, exactly. Exactly. The answer is waterfilling. But
Assume it's a memoryless channel. I mean, each channel state is independent from time to time.
yeah, exactly. Yeah. So you do waterfilling.
It doesn't have to be memoryless.
It doesn't. Exactly. Yeah. It
Have any
doesn't.
memory you want. It's still
Okay,
waterfilling.
but in eigenvalue.
Yeah. So okay. So actually, so you're kind of this is a wonderful segue. When I have a memoryless channel and no buffer, right, and I have perfect channel state knowledge, waterfilling. Even if I have memory, the answer is still waterfilling.
Yeah.
Right. So now let's see what happens when I put the buffer back in. So I still have stochastic arrivals, and I have a memoryless channel, and I want to still solve this problem. It turns out this also has been solved. Okay, and I'll go over that. Again, the answer is a waterfilling type of solution. Okay, so the new thing here, or the different thing here from the existing piece of work is, it turns out in the stochastic arrival case with correlated fading, right, with channel with memory, the answer is not waterfilling anymore. And so this is what we do. We characterize the structure of the adaptive policy with correlated fading. And on the previous page, actually, I said we're adapting with MQAM. I mean, you could assume it turns out that the characterization of the policy holds for a wide range of different types of power functions, right? This MQAM just determines what power I need to guarantee certain quality of service, like bit error rate on the physical layer. You could use Shannon capacity, pick any other modulation scheme, but as long as it has as long as this power function is inversely proportional to the channel gain, these results hold. Our simulations are for MQAM. So we characterize the structure of this optimal policy with correlated fading, and then we just compare the performance of this adaptive scheme with some other less adaptive schemes, namely waterfilling. Okay, so we formulate the problem as a Markov decision process. This is pretty standard stuff, actually, this formulation here. So my system state is going to be the number of bits in the buffer at time I, and the channel gain at time I. And my policy is a map from the system state to number of packets to pull out of the buffer. By the way, you can let BI be bits or packets. There's a simple way to translate. So sometimes I may say bits or packets. The simulations are actually for packets. So this is my policy UI. This is what I'm actually interested in finding. Okay. So my immediate cost. So I define this thing called the immediate cost, which is a function of the system state and the policy, and it's a linear combination of the power that's needed to transmit VI packets when there are UI packets when the channel gain is GI at a certain quality of service, and this is the probability of buffer overflow when there are VI packets in the buffer and I pull out UI packets. Okay. Now, somebody who's really paying attention, or somebody who knows this, is going to say you're not solving the actual problem, and that's why we're not. Now I said I want to minimize the packet loss rate due to these constraints, and this is not exactly doing that. But it turns out you can prove that for given value of data, if you solve this problem, you get a solution on the optimal trade-off curve. So it's sufficient to solve this problem. Meaning this gives you what's called a Pareto optimal point. Okay, so we take the immediate cost and we define our actual cost function, which is an average cost, which is defined as it's a function of my policy. And this is the problem we want to solve. We want to find the policy that minimizes
the problem you started with was you wanted to maximize the average rate subject to.
Now I want to just minimize the packet loss rate.
You wanted to minimize the packet loss rate, which is the buffer overflow.
Yeah, exactly.
The buffer overflow, subject to meeting a rate constraint on the subject to power.
Power and yeah.
So you just get whatever rate you can on the channel. but your goal really is
no, I mean you want to maximize the rate. That's implicit here. Yeah, I mean, given that you need to,
it's indirectly implied by minimizing the packets lost in the buffer.
Yeah.
That you want the rate to be high.
Right.
But exactly the way, I mean, I think what you're going to have is policies, right, where when the buffer is very full, you're going to do something that is somewhat different than than the most efficient rate maximizing strategy
right.
in the air.
Yeah, that's right. Yeah. Okay, so let's go back here. So when we actually do the simulation and we show the performance curve, we're solving this problem. We're finding the policy that minimizes this using dynamic programming techniques, policy iteration, so on. Okay? To actually prove something about the policy, we go to sort of a slightly different way of doing things. We define this thing called discounted cost, where you define your cost function by discounting the future cost. So you have this discounting factor alpha. Alpha is less than or equal to 1. And you then say, I'm going to find the policy that minimizes this. It turns out that if you can prove something now the one thing to notice is that the solution of this matches this when limit as alpha goes to 1. So if I can prove something for all alpha, then I've proved it for the average cost problem. And so when we do the structure, we have to work with this, because this satisfies a nice sort of implicit equation that you can exploit to get information about the structure. But we prove it for all alpha, so therefore it holds for the average cost problem. Okay, so remember I said two things. Look at the structure of the optimal policy, and we're going to look at comparing the performance to sort of less adaptive schemes. So let's look at the structure. So the question, how does the optimal transmission rate depend on the buffer and channel state? And when the channel is memoryless, this problem was answered in 2000 by Randall Berry. He looked at, instead of buffer overflow, he looked at delay. But it's very easy to sort of go between buffer overflow and delay. And in fact, right now, we're looking at delay because you can, actually, it's a little bit easier to work with. But in this talk, it'll be a buffer overflow. But he showed that the optimal rate is monotonically non-decreasing with buffer occupancy, meaning when you just adapt to the buffer alone, right? No matter what the channel is, remember, when you adapt to the channel, you get a water-filling type of solution. When the fading is memoryless and you adapt to both channel and buffer, again you get a something that is water-filling like. Okay, and so in the context of our work, we did that. So this is a memoryless fading. And you notice that as sort of the channel gets better, pull more bits out of the buffer, right? So these 4 curves are for sort of the initial state of the buffer. There are 15 packets in the buffer, 10, 5, and 1 packet in the buffer. This is the channel state going from bad to good, right? That's the outage state. And this is the number of bits that are mapped to a QAM symbol. So this is determining how I'm emptying the buffer. Okay, it's affecting my modulation, my constellation size. So there's the rate control. Okay, and so this is with memoryless fading, and we get a water filling type of solution in the sense that, I mean, it has all the characteristics that below a certain threshold you may not transmit. It's not worth it to transmit, right? And above it, you sort of increase as the channel increases, as the channel gain increases. Okay, so this is the policy for memoryless fading.
So does everybody understand this? Looking at like.
Yeah, I forgot to mention this in the beginning. Please feel free to ask questions anytime. You don't have to wait. So if you guys have any questions.
So the associated with each one of those circles, you have a channel state.
Yeah.
Then there's some power level that you decide to use. But essentially you're choosing a constellation size.
Yeah. Right. And then we choose the power to guarantee the quality of service, bit error rate. So with NQAM you have, you can derive the probability bit error as a function of the constellation size and signal to noise ratio.
So then the power is given by, oh, you have the constellation size with some bit error.
Yeah, but we have an average power constraint.
Right, but that only affects you from symbol to symbol in the sense that, that on average you have to use the right power.
That's correct. Okay. And so this is just random variance work. I mean, in our context.
So how many packets were? Oh, okay. So it's the average write rate is one packet. A frame is the unit of time in which you do this.
Right.
So if you start with 15 packets.
Yeah, in the buffer. So my buffer length is 20 packets. So it's very full.
Is channel state 0 the channel state where the gain is 0 and nothing goes through?
Yeah, exactly. It's complete outage.
And then
there's no way to transmit on this channel.
So what's channel state 1?
I actually, to tell you the truth, I don't exactly remember. This simulation was done by my student, but essentially we have this finite state Markov channel. Yeah. We have 8 states, and I think it's just sort of. I mean, you want specific numbers, right? I guess.
Well, I just was wondering, like it's funny how I think channel state 1 I look at must be fairly decent because with 15 packets, right, you'll decide to
pull 4 out.
To pull 4, yeah. That seems like a lot, right? So anyway,
so this is with memoryless fading, and this is not new. So what is new is that when you look at correlated fading, right? Again, the reason we did the other curve was because this is in the same format. We have channel state here, a number of bits here, and again the same 4 scenarios. We actually find that the policy is no longer monotonically increasing in rate. I mean, it's not waterfilling like. And it's kind of what you said. As when the buffer gets full and the channel is in a bad state, you have to maintain a network layer requirement, which is in this case probably a buffer overflow. Right? So you pull packets out of the buffer no matter what. And so as you move towards the outer stage, you actually pull more packets out of the buffer. And this is done by simulation, so you can characterize this. Using the discounted cost, you can prove this will happen.
What do you mean it's done by? So I would assume that
this is solving the average cost problem.
Right, but you do like policy iteration.
Exactly, yeah.
It's not simulation, it's iteration.
That's what I mean, yeah. I mean that we are solving the problem, so we can actually prove that this will happen. You can characterize. Exactly, so that's what I mean, yeah. I mean, this is like
calculation.
Calculation, not simulation.
Programming.
Exactly, that's what I mean. Sorry, not I mean numerical computation of the average cost problem. But if you use the discounted cost formulation, you can actually prove that this will happen. Okay, and so let's see what happens when we compare it to 2 other schemes. One is fixed rate. It's just essentially it's smart channel inversion. You just invert the channel to keep constant SNR. And the other is waterfilling. We adapt to just a channel. Okay, and this is there was a 97 paper by Goldsmith and Chua in Transactions.com that proved this when you adapt to the channel. This is the optimal thing to do. Okay, so this is plotting on the x-axis. We have the average power, and we have the packet loss rate. This is probably a buffer overflow. For the 3 schemes, again, the optimal is so the blue is the dynamic programming solution. Black is fixed rate, red is the channel adapted, and we see, well, first of all, we see that actually the optimal is, it gives you a lower packet loss rate for a fixed average power across the board. Okay, so I mean, sort of, it's sometimes nice to see things working out. So this is the case. It does beat both these things that are less adaptive, and this makes sense actually, right? What's interesting to me though, this I couldn't answer. If I look at high SNR, right? So what got me thinking wasn't actually this. What was this? Was that doing nothing is better than adapting the channel at high SNR. I couldn't really answer that. So I don't know, right? Because remember, this is waterfilling, right? And this is the fixed rate channel inversion. But smart channel, and smart channel inversion says that I don't transmit when I don't have data.
But otherwise, you just invert the channel.
Yeah, exactly, to maintain a fixed SNR.
And you have to choose. So how do you choose what rate to adapt the channel?
The average power constraint.
So it's basically you're on-off.
Yeah.
An on rate or you're off, right?
Yeah.
And with the on rate, like you look and say, oh, I'm on for this set of states, but given I'm on for those, there's some average power.
Yeah,
and
right.
Then you have to. Do you have some? I think you have some probabilistic policy at one channel state where you have to be on only some of the time to exactly meet the average power constraint.
You have to be on.
Well, like so, one of those channel states, right? You would have to have a probabilistic. I'm on sometimes and sometimes I'm off, in order to exactly have your average power be whatever PAV. Agree? If it's a discrete set of states, because otherwise, if he says, "Oh, I'm going to be on at the fixed rate at these states," then his average power is something it may not be exactly.
Is the fixed rate on-off truncation, inversion, or just?
And fixed rate is just channel inversion. Whatever the channel is, I make up.
Channel.
But you invert it for some QAM constellation size, which you optimize over or you set beforehand. You remember?
I have to think. Yeah, I'm not exactly sure of how to answer that question right now.
So maybe the difference is in there. Maybe if they. So it seems like you could choose one rate, right?
Yeah.
And then be on for more states, but at a lower average rate.
Yeah.
Or choose a higher fixed rate and be on for fewer states using the same average power. And your mileage would vary, right?
Yeah. I mean, so basically, you're saying that because we're not optimizing over spectral efficiency.
Well, it's all that.
We're optimizing. I mean, that's what it seems to me like. So maybe the answer to this question is that here we're minimizing packet loss rate.
Yeah.
And you get. I would have thought these would have the same spectral efficiency, but maybe there's something else. Maybe they're not. I mean, if they weren't, that would explain this.
Yeah.
Question.
Yeah.
The 8 channel states, are they 8 different gains? Yeah. And are they uniformly? Okay.
Well, the question is, what's that mean? Is that uniform in dB, or is it equally Leo? Yeah. But I think that might also matter.
It probably matters a lot.
Yeah.
Because if you had a Rayleigh type distribution, you get very different results. I think the channel inversion wouldn't work at all.
Oh, I see.
Because
I'll have to check exactly what.
Well, he truncates though.
I know.
Right?
Yeah. I know, but I mean, if it were truly a Rayleigh distribution. I couldn't do channel inversion.
Well, there's some
base would eat up all your average power.
But he would turn off first, so he has a choice at whatever rate, like the worst states, he would turn it off. So he has another parameter there to.
No, I think he used to have the same average, same rate, the same average rate. Otherwise, it's not a fair comparison. Right?
Well, the fair comparison is that ultimately is that they use the same power. That's the physical thing.
Yeah, and they are. Like when you are at this.
It's the same average power over time.
Yeah.
Right, and everything else I think is up for grabs.
Oh, I see. Okay.
Right, in terms of.
Yeah. But anyway, so okay, so that was it. So the takeaway points are that when you adapt to both the channel and buffer, you get better QoS of both the physical and network layers, right? Meaning that for fixed average power, I can get a lower packet loss rate, and for a fixed packet loss rate, I need less average power. And the structure of this policy can be different from other policies that adapt to only channel. In this case, we saw it was kind of I mean, you sort of guessed it, right? That when the buffer is in a dangerous state, you're going to do something different. Yeah, and so it turns out that is the case. Okay, so so remember, so this was only single user, and we're actually currently working on trying to formulate this in a multi-user environment. Okay, so So the next topic is sort of related to this thing. It's not the same exact problem though, but it is a multi-user problem. We're going to look at this thing called multi-user diversity. I think probably many of you know this term, right? Am I right? Or can I? So get an idea if you guys know what I'm talking about? When I say multi-user diversity.
There's a real record tradition that students never reveal they know anything, right? But I would say 3/4 of the room knows exactly what you're talking about.
Okay, good. So, this is not, actually, this is kind of a logistical thing. I have slides. I'll skip a bunch of slides if people know what multi-user diversity is. You know, there's no point in sort of saying the same thing to people who already know. So this is what I'm asking. Okay, so the outline for part 3 is we'll look at the motivation for the problem. We'll look at existing, or maybe quickly, existing forms of multi-user diversity. Then I want to point out actually another instance. And this instance shows up when you consider the different layers. Okay? So this is another instance of multi-user diversity, and we'll look at some results. Okay, so creating channels. Okay, so this is kind of an important point. When you have point-to-point communication, the traditional approach is to create reliable links, right? By either doing things in time, TDMA, FDMA, CDMA, right? And you deal with fading, you compensate for it by these different techniques. In 95 and 97, for the uplink and downlink respectively, these authors showed that if you want to maximize the information theoretic capacity of this multi-user system, that you actually don't want to orthogonalize, don't want to create multiple point-to-point links. You actually want to take all the channel resources and give them to the user with the best channel at any time. And this is what they called multi-user diversity. Actually, it's Raymond Knopp in his thesis called it multi-user diversity. Okay, and so comments here, but the important point, it turns out it's essentially under the title of orthogonalization, but it's a channel dependent. The channel decides how you orthogonalize users. So it's a time division type of process. Except you don't decide, the channel decides. Okay? So this is, so multi-user diversity is essentially that the intuition is that when you have a large number of users, there's very likely to be a user with a good channel. And users have random, if the links between, if links of all the users are sort of time varying randomly or independently, then the best user changes. It's sort of like a hot potato, right? If, let's say, I have a hot potato, I can't hold it for that long, I throw it to you. You can't hold it for that long, you throw it to him. Having the hot potato means I can use the channel. Right? So it's changing, and so you get long-term fairness. And so this is what the authors called multi-user diversity. And the interesting thing is that they call it a paradigm shift, in the sense that you're not compensating for fading, you're exploiting it. And actually, you know, in some sense, single-user waterfilling is also doing something very similar.
Oh, yeah.
Right? I mean, it's taking advantage of the time-varying nature of the channel. So, to be fair, actually, this notion existed before. It's not really all that new. But anyway, the authors sort of make this concrete in a multi-user setting. They prove that this thing maximizes the information theory capacity. Okay. And so this is a quick example. I'm going to skip over all this. So in downlink scheduling, so in downlink I have, let me look here. So downlink, I have my base station here, has data for all different users, and I have to figure out how to send, which user to send data to. Maybe it has there's some multiple access scheme, it sends data to all users, or maybe it uses this information theoretic scheduling where you send to one user. But whatever the case, it's a scheduling problem. And we find that, so here's a curve that this is David said in 2000. And this is my sort of manipulation of it, but the data is his, and the idea was from his paper. As you increase the number of users, we're going to look at the increase in throughput over round-robin scheduling. Okay? So round-robin is I just give everybody in turn, and the HDR scheduler is actually, it's essentially the transmitting to one user at a given time, but you introduce some hooks and handles for fairness. I'm not going to get into that right now, but you want to guarantee fairness in some time, not an infinite time, but in some finite time. So some hooks and handles to guarantee fairness. But at its base, it's the information theoretic scheduling, what some people call non-public scheduling. But we see that the improvement over round robin in a fixed environment is modest, and eventually, as the number of users increases, it flattens out. But when I have a mobile environment and I have sort of lots of time varying fluctuations on my channel, actually this increase skyrockets, right? This is a percentage, right? So you get 200% improvement in throughput if I have 10 users, right? So sort of, if you will, sort of putting the idea into practice and seeing it does work. There are many catches actually to this, and fairness is one of them. So anyway, this is just sort of one view of the work. Fading is bad, must be mitigated. The supposedly new view is that fading can be exploited, and the more random the better. And if your channel is not random enough, there's some work done in 2001 which says make it random. Okay. I was talking with someone about this, and they said this idea actually was proposed a while back by somebody at Lucent or AT&T, which I can't remember. Do you know about that? This idea of random.
You heard people say whenever they talked about blast, right? That, I mean, this is, I guess you would hear people say in 98 or 97,
yeah,
they ought to randomize the channel and float, clutter in the air, but I don't know if anyone actually,
somebody mentioned that,
actually proposed doing
because this is my first, interaction with this, so I tend to say it was done by them here, and so we said no. And I mean, I don't really, they didn't provide the exact reference, but I just want to be accurate in
well,
what
you don't remember any specific. They certainly talked about it though, about that.
Sure, because the math shows that the channels are random and uncorrelated. You get more.
Right.
Yeah. Okay, that's obvious, or is something that you know of a reference?
Well, this comes out of the theory of multiple input, multiple output.
Okay.
So I can give you a couple of references.
I mean, I think
Porcini did that, right?
Yeah, right.
Yeah.
Okay. Anyway, so again, and another example, again by David Say again, where it's another instance. I guess what I'm trying to say is there are some existing instances of multi-user diversity, and what I want to point out is another instance. Okay. So what is that other instance? Oh, the other instance comes out of actually looking at this as a view of trading off fairness and efficiency. And the interesting thing is, I didn't think about it like this until I tried to explain this to my sister, who is just finished her MBA. I was talking to her about, she wants to know what I'm working on. So I told her, and she goes, "That's simple. That's just trading off fairness for efficiency." So anyway, I like that notion. So let's see what we mean by that. Like why we are trading fairness and efficiency, because I told you there's a catch to the non-public scheduling, and the catch is fairness. Right? You cannot guarantee fairness except in this sort of long-term sense, that if the channels are fading randomly, eventually everybody will get the chance. But there's no guarantee. But this is what maximizes the system efficiency, right? Because as far as the system is concerned, all the users become a virtual user. Right? And so you give, and when the best user transmits, this virtual user is using the resources to the best that they can be used. Right? So it's maximizing the system efficiency. Right? And so we get into, so if I want to look at efficiency, I get non-optimal and say, if I want to be fair, I've got to start going on the other side, do some sort of generalized processor scheduling, max min fair wireless there's wireless fare scheduling and so on. Okay, so these are efficient. There's no delay guarantee. These are fair. They give everybody maximum will maximize the minimum that any user gets, but they're inefficient. Okay, so this got me thinking about what else. How else can I trade this up? And so the example we gave is an octane scheduling. So once again, we have base station. We have multiple users, right? Who are it's uplink, so multiple users translating to a base station. These users have stochastic arrivals, and they're buffering their data. Now their buffer states are time varying, right? And so what we want to do is we want to exploit these time varying instantaneous buffer occupancy. Can we exploit this thing to increase some performance measure? And essentially this is a single server, multiple queue schedule control, right? Because I have my base station being my single server, I have multiple queues. And we're going to look at initially at 3 schemes, round robin. We'll look at max min, okay, which maximizes the minimum that any user gets. And we'll look at, so the not-pumlet scheduling gave the channel to the best user. So the heuristic analog of that in this case, I call max buffer. I let the user get the maximum buffer occupancy trend. Why? Because I'm interested in a network layer characteristic, buffer overflow, right, or packet loss rate or delay. And the user with the largest buffer is in danger of violating that the most. And so we look at max buffer. Okay?
I want to thought that's almost the opposite.
Exactly.
Because I would have thought the person who is the max buffer is maybe someone who, if you have anything that favors people with good channels, then the person with the max buffer is the person with the worst channel. There's some correlation between a full buffer and a bad channel.
Yeah.
Because
and
it's almost then if you want him
to. But you have to look at
channel inversion.
What the metric? What you're saying seems right. Like we just look at max, min. Large channel gain is good, so low buffer, right? I mean,
so it means.
But I think when you look at your metric, right? In one case you want to maximize capacity. In this case you want to minimize buffer overflow. So I mean, so there's an inversion there. So one could argue that the max buffer is the max channel gain. I don't know, maybe.
So I guess I have a predisposition towards thinking that what you want to do is exploit the good channel.
Okay.
And then I think, well, if you're doing that...
No, you're absolutely right, but this is the point I'm trying to make. I'm trying to say this another instance. So in fact, for the next 2 slides, we're going to assume a static channel.
Yeah.
And I'm going to show that you can still exploit this. And then later, we'll show that when you combine this with not-pumlet scheduling, you can do even better. I mean, your point is exactly right, that you want to exploit both, but...
That's a good point. Actually, most people, they're doing a lot of scheduling schemes, such as max, what they call it, maximum largest related delay first. Or alpha rule, or exponential rule, all those kind of scheduling are trying to combine the powerful queuing process with the chaining process.
They are. But in all of the work that I've seen, when people talk about multi-user diversity, they always talk about exploiting the channel gain. I mean, they may include some, I mean, I need to get this reference from you, but I'm pretty sure I haven't seen anybody say, oh, this is another instance, like, let's put it on a static channel.
But don't you think so? If you say the static, the channel's static, and now you're doing this max buffer policy, and somehow the overall packet drop rate is smaller, right? It's sort of like a backwards or an inverse version of like of Erlang trunking or something, right? Like, if you think about, like, you can have a bunch of different sources all with their own buffers, right? And they all get their own blocking rate. And if they could merge their buffers into one and have one big buffer, of course the blocking is much, much smaller.
Yeah, but you can't do that here.
Well, no, but here effectively what you're doing is you're sort of thinking about all the buffers of all the people collectively.
Okay.
Right?
Yeah.
And the result is that the collection of buffers acts more like one big buffer than just like an individual user with an individual buffer and some individual process of emptying it. It's not exactly the same.
I guess I don't see it that way.
So I shouldn't interrupt you.
That's okay. No, I'd like to if there is a sort of an effective view here, I guess I don't see that.
Okay.
We can talk about it. Okay, so let's see what happens. We're going to look at the static channel. Okay, so just additive white Gaussian noise. We look at system load. So this is it has 5 users and buffer length of 4. Each user has buffer length of 4. And so this is just done by simulation, okay? We're going to look at the 3 schemes: max, min, fair, round robin, and max buffer. And we're going to plot the packet loss rate, the average packet loss rate, versus the system load. And well, we see that max, min, fair, which tries to be the most fair, is the least inefficient, right? In the sense that the packet loss rate is the highest. And the max buffer is, for a given system load, it has the lowest packet loss rate, right? And actually, I think you can, in multiple server, in single server multiple queue problems, there's this longest queue first scheduling, and essentially that's what max buffer is, right? And I'm not sure what you can prove about longest queue first. Do you know what you can prove about it? Can you? I mean, that's what we're trying right now to see if we can prove this is the case. This is simulation. We're trying to prove that this will minimize the packet loss rate. I haven't been able to find a proof of it.
So you know that earlier scheduling the fair amount of queries that
it's similar.
Conditions prove that it is the optimum.
Yeah, it's similar. It's not.
Not exactly.
Yeah. Okay. So, but again, we're so this is on a static channel with 5 users. Let's see what happens with 10 users. Right? Remember, multi-user diversity, there were 2 components. One was that the gain increases as the number of users increases. So 10 users, with a buffer length of 4, and we see that the gap does increase. I'm going to compare these 2 on the next slide, so don't think too much. But with 10 users, we sort of see the same trend, but this gap is much larger. Right? So this actually got me thinking. When you think about point-to-point channels, you talk about capacity. Right? When you have unbuffered, you talk about capacity maximum rate. Is there something like that for buffered communication? And well, the thing I came up with was actually my x-axis. My system load is what the system cares, or is what the user cares about. How much data, at what average rate can I pump stuff in? Right? So maybe that's a good measure of quote unquote capacity. I mean, not capacity in the sense that we can prove a coding theorem, but something that the user cares about. So let's take those 2 curves and flip the axes, okay? So, yeah.
I saw your packet length is 4 packets.
The buffer length is 4 packets, yeah.
What does that mean?
It means that the users have a buffer of size 4. Because we're on calculating packet loss rate, this is done by simulation.
Okay, what's your capital variable first?
Let's see. It is. I think we're just assuming for the simulation Poisson arrival.
Yeah, it seems strange to me because max min fair may be performance may be better than round robin.
No, I don't think so. Because of the notion, because you're trying to be fair.
Sorry.
Yeah. Okay.
Okay, that's still okay. Sorry.
No, don't be sorry at all. No need.
How much delay you assume in getting the buffer feedback?
Sorry?
How much delay is there from?
Yeah, okay, so right now we're assuming instantaneous knowledge of buffer occupancy. We're looking at what happens if you get delayed feedback and estimating.
There's also problems with this scheme that it's a very volatile measure, and as it feeds back, if the delay is too large.
Yeah, definitely. Yeah, we'll find that it's very sensitive to having accurate information about. No, actually, let me think. With this, I've been away for about a month, and my student is it was looking at delayed feedback, and I think the last thing that he said that if you're off by not too much, there's not much difference. But I'm not. I mean, we haven't characterized it. Okay, so again, like I said, I wanted to look at something that made more sense to me. So my y-axis, I want to put admissible system load, because this is sort of a measure of what the user cares about. Okay, and we look at buffer overflow. So now I can ask the question: for a given buffer overflow requirement, what is the maximum admissible system load? Right, and that's a nice question. The question of, for a given SNR, what is the maximum rate at which I can transmit? And so, just taking those two curves on the previous page and manipulating them, we get sort of a nice view that here's the 5-user case and the 10-user case for max buffer. And we see that for a given buffer overflow requirement, we can admit a higher system load. So this is sort of, I think it's fair to say this is another case of multi-user diversity. Or something is going, you're exploiting the variation in the fluctuations of the user's buffer. Remember, this is on a static channel, right? So let's see what happens on a time-varying channel. So now we want to do with buffer and channel adaptive scheduling.
How do you normalize the? Yeah, is that load per user?
Yeah, it's averaged for all the users.
So in the 10-user system, like, is there 10 times the load,
No,
10 times the bandwidth, or is it that there's the same load as in the 5-user system, but the arrival rates for the 10 queues are half as much? Because, like, if the overall packet arrival rate is the same for the same load, right, then 10 is always better than 5.
Of course, yeah. No,
they have more buffer per arrival.
No, so you're talking about, like, if you think of this as a virtual user and like the overall packet arrival rate. I mean, the overall packet arrival rate is going to be, there's more packets coming in when you have more users.
Then somehow, so for the same, like for 0.85, for 10 users, the arrival rate is 10 times 0.85 of something.
Yeah.
And the other case is 5 times 0.85.
Yeah.
But then there's a question of what the channel bandwidth is. Like, is the channel bandwidth scale 10? Because otherwise, otherwise the system 5 times 0.85 into the same channel bandwidth, you're much better off.
If the channel bandwidth is the same, you're saying?
Yeah, right. Because that's everything.
Is system load normalized?
Well, so the question is, something is normalized, right? Is there a bandwidth?
No, the bandwidth has to.
normalization?
I mean, it has to be. In these two cases, I would expect the arrival rate is half when k equals 10 if the packet size remains the same.
The
bandwidth has to
arrival rate
arrival
per
rate.
queue, right?
And that's why you get the large gain when you go to 10, because if you have packets
Per buffer, right, with the same size buffer.
There's more statistical flex, but that's the second.
Right, but the big gain would be the fact that the same size buffer is half the arrival rate today. So that's the way I would thought, but then, somehow
I don't think that's what's going on.
But then if you say,
You have to double
it's
the
double
bandwidth.
the number of users, do you double the bandwidth? And
Or the
transmit things twice as fast?
Let me think, hang on. I mean, that's essentially doubling the balance. Right?
Yeah. Right.
It has to be otherwise.
Well, if that's the case, no, I'm trying to think. Hang on.
Now you have a UMTS channel or something which is 1 megabit. You have to normally.
Yeah. Sorry, it's double the bandwidth.
Yeah, that's what I'm saying.
Yeah, it's double the bandwidth. Right, exactly. Yeah. But it's not. I mean, but that's not equivalent to saying having the arrival rate.
It might be. I'm not sure if it is or isn't, but it seems like it might be, because then you're sort of like, you're doubling the bandwidth and the arrivals per unit transmission time, then maybe it goes down.
Think about it.
I'm not actually sure.
Think about it. Equivalent. Okay. Good questions to think about.
Yeah.
Okay. So okay, now we want to adapt to both the channel and the buffer, and so now we're going to compare a few schemes again, still with max buffer. Now, since the channel is varying, we actually go to max gain. Right? We can adapt to the channel gain. And then we look at this sort of ad hoc scheme, this hybrid scheme, which says when the buffers are lightly loaded, I'm going to do max gain. So just some threshold. And when they're heavily loaded, I go to max buffer. So it selects between the two. It's not the optimal policy we're working on. What is the optimal policy, scheduling policy in this case? But having finished that yet. But so now I'm going to look at. I'm not looking at system load here. I don't have that here, but I can infer the results from this. So on the x-axis we have average power. The y-axis we're looking at the overflow probability or the packet loss rate. And the three schemes, the blue is the hybrid where I switch between max buffer and max gain. Red is max buffer, and black is max gain. And well, so for a large range of average power, we see that the hybrid does better than both these. So when I even just do a simple adaptation, a simple combining of adapting to channel and gain, meaning I selectively choose, I can do better than both. We haven't optimized over the threshold. I think we just picked some threshold to call it lightly loaded or heavily loaded for this graph. But we see that if my overflow if we're given average power, my overflow probability is less, I can admit a higher arrival rate. Right? So if you plotted the admissible arrival rate, you would see that it's larger for this here. And this is
so you get kind of results where we're very low power. It looks like like ultimately you want to save power, you go to max gain. Yeah. But it seems like there'd be another category of if you replotted for higher power the results for bigger buffers. You would get eventually in the limit of infinite buffers, you should also get max gain as your best power.
Yeah.
So there'd be some place.
Yeah, nice limiting things. Yeah.
Well, there's some buffer size where the black one becomes the best again in terms of the trade-off.
The max gain.
Just because in the limit of it.
You see, as the buffer size gets large.
Yeah, as the buffer size get large, eventually, well, I don't know how it overflow. Maybe they would never cross, but they would all just go to 10 to the minus something large.
Basically, by setting the buffer size limited value, you are putting a corridor service requirement on each users. So by putting those two schemes together, you're using hybrid, right? Yeah. So you are trying to trade off between QoS and efficiency. Okay, that's the fundamental point. What the current literature actually, people have already done similar work. They simply put the current Q size together with the gain, the channel, multiply them together, and based on the value product.
Do you think they multiply the buffer size times the channel size?
There is one. It's ad hoc.
Yeah, I mean, it's ad hoc too, though. So right.
They got a lot of mathematical background now. That they basically
multiply. What's the reference?
I will give it.
Will you send it to me?
And
so who are the people who have proposed the multiply?
WINLAB's mathematical department.
Soliar? Has proposed the multiply? Probably a good idea to be proposing it.
Yeah, and later people extended that to even further, exponential large division theory.
Yeah. Soliar's a really smart guy. He just multiplies, he's probably right.
They call it throughput optimal.
Okay, I don't know about this. Yeah, I'm interested.
A lot of people are doing a lot of things.
No, there are. Yeah, I mean, a lot of people are looking at this, but like I said, my view is, the approach I took was looking at this work and seeing it as fairness and efficiency, and noticing that That's another thing that can be exploited. And like I said, and all this doesn't work.
Do you have any sense of what kind of buffer length is meaningful? Like, you're using numbers.
No, we use it because we want to get.
No, but that has to be normalized to the arrival of it.
Yeah.
Exactly.
But should it be 50 or 500?
Normal is very large.
Normalized, you want it like, n times the
well, in a cell phone, you have some good reasons for making it small.
Yeah,
versus a laptop computer.
Yeah.
This is delayed and.
Yeah. No, I mean, in practice, it's large, right?
Well, I don't know, you chose 5.
But again, like I said, it's normalized to the arrival rate. And I think you would get the same result if you scaled both of these appropriately.
Yeah, right, but even normalized the arrival rate. Like,
what's reasonable?
Yeah, what's reasonable?
I
don't know.
Yeah, I mean, to be honest, 5 was chosen because I don't have this long time running simulations.
There is a scheme they choose the buffer size. Following the what they call it, the virtual buffer.
Yeah.
It's just like a token bucket, leaky bucket.
Okay.
And the minimum rate is feeding into the bucket.
Okay.
And the buffer virtual bucket will be drained out by your service. Somehow they based on the maximum size and based on the size of the virtual buffer for each user and each user's channel gain. Based on that, they do the schedule. That's very natural. I think that's very smart. Then you don't need to worry.
But then the question is,
the buffer size is the maximum size of the virtual token, and this one.
Yeah. But there's some notion in there even of how big should the bucket be?
Well, usually it should be decided by your delay tolerance.
Okay.
Yeah, that's what I was saying.
So
the question is, if buffer size, then it's not game policy.
So your view is like you look at some applications and figure out what their packets are and what delay that corresponds to, and then that really says what your buffer size is.
That's right.
Okay.
And then
What's the difference between optimization based on the delay and based on the buffer?
Yeah, no.
Maybe not, but he sort of said earlier that there's not so much difference. I think that.
No, there is.
Yeah.
In fact, like right now we're looking at delay because you can prove it's easier to prove certain things for delay. Okay, so that's it. So the sort of summary in reverse order for the multi-user diversity. When you adapt to both physical and network layer characteristics, you get a higher admissible system load. Right? So in a multi-user case, each user can pump in data at a higher average rate if my scheduling policy adapts to both physical and network layers. That's sort of the conclusion we made from here. For the cross layer, for the single user, we saw that we can get a better quality of service for both layers when you adapt to both physical and network layer. And for so what seems to be a purely physical layer issue, but I think it has a role to play here, how we're thinking about it, which is, when you're doing spread spectrum or not, you want to beware of spreading at high spectral efficiency because you will be far from the shadow limit. But remember, spreading has its benefits, and you might want to do it anyway. Okay, that's it. So any questions that is burning to ask?
I have a few questions.
Yeah,
First question is when you're saying that spreading of knots, in that case, if you do not know channel, what's going to happen? So have you ever thinking about that? Because when you actually calculate those values, assume the channel is.
Yeah, it's assuming ideal coding, decoding, yeah.
Right. So then the potential question is, if you think about a gap analysis. So basically take the log n and the value has not just over a gap value. So basically the graph is shift to the left hand.
Yeah.
So basically it seems like the conclusion may be something like we may not care about it.
No. So if you don't know the channel, right, you have a slightly different problem. Okay. You better now pick a receiver. Right? It depends now on your receiver. Right? Because if you do, mass filtering, don't care about the channel. if you do like MMSE, whatever, you need to know some information about the channel, right? So it makes a difference on whether your receiver depends on that or not. So you guys now pick. There's some work that we did a few years back, on like this coding spreading trade-off, and there, we looked at this issue of, what happens when you choose, and then we did the single user. This is work with Venu.
Yeah.
On single user, you have basically have single user encoder decoder, but with spreading and joint despreading, if you will, like MMSE type things. And in there, you can sort of ask the question. In there, when you have perfect channel knowledge, it turns out that the spreading with multi-user detection is not that much better than just doing coding with mass filtering for the fixed bandwidth expansion. But as soon as if in that problem you include channel estimation, the MMSE suffers, whereas the coding mass filtering really doesn't. So it changes your conclusion a little bit. You got to pick a receiver now. I think as soon as you start talking about channel estimation, is that?
No, I agree.
Is that fair? Actually, there is some work done by Nero and Medard on the capacity of the multiple access channel with channel estimation error, and there's some work with delayed feedback and so on. There's all bounds. It's very difficult to get an analytical handle on that.
Feedback or speakers?